All right, so I'm John O'Donovan, and I'm here to present a paper that speaker just announced. I can do better than your AI, expertise and explanations. Before I start, I want to give just a quick caveat that these slides were given to me about a couple of days ago by a student who's registered and just couldn't make it for an external reason. That's the first author, James Schaffer. I'm familiar with the study, but if there are a couple of questions if there's some questions I can't answer, I'll have to take them to him, but I'll do my very best. So the study was conducted at UCSB, UC Santa Barbara a couple of years ago, and the analysis was done more recently by James while he was at the Army Research Lab. So well, I'll start by saying it's really interesting that a question came up about novices and experts and how they can be convinced, and I think that was a really great segue from the previous paper into this one, because I'm going to report on a study that actually found results that really answer that question in some way. So the outline is I'm going to just introduce the general idea of the experiment that we conducted to understand how humans interact with AI. I'm going to talk about, just kind of introduce the topic. I'll do it briefly because it's similar to the previous paper's introduction. Then I'm going to describe an abstract trust game, an experiment with an abstract trust game, and then talk about some results and conclusions. So just a little bit of background, and this you can see the similarities with the previous paper here. AI cognition and human cognition are obviously really different. It's a really common context is where an AI's role is to filter some information, and typically a human can in turn provide some control or feedback to that AI. It can be done kind of implicitly or explicitly. Also, there's AI can have a certain types of state. So let's say, for example, the AI's task is to predict a recommendation for a movie or a book or something like that, a score. And if all the pieces of data in the training set for that AI, they all say it's 3 out of 5. The AI can be fairly confident, like there's lots of 3s, fairly confident recommending a 3. But if the AI had a training data set that, let's say, had lots of 1s and 5s, was polarized, it might not be as confident. Or, for example, if it just didn't have enough data, it might not be confident. And in these cases where AI is uncertain, maybe it's better for the AI to try to explain itself and communicate some of this uncertainty to the user. And in practice, what this becomes is a kind of interactive dialogue that goes on between the AI and the user, where really the human is assessing the AI with the purpose of making some decision. And there are things like interactive states like trust that come up. And what typically happens is, this process goes on, maybe 1 or 2 iterations, or maybe many iterations if it's a more complex task. And eventually the human decides to halt the process and come up with some decision. And the analysis or the analogy that James gave here was, can we predict the weather? Weather's extremely complex. We build models to do that. It's not always perfect, but at some point the meteorologist says, okay, it's good enough, let's publish this in the news. Okay, so there's been lots of prior work in these areas kind of individually. This is obviously an intersection between psychology and computer science and cognitive science and so on. There's been lots of work in explanations for AI, and we're seeing a hugely increasing amount in that now. Automaticity, lots and lots of work on error and accuracy in AI, like Netflix Prize and so on. And then even work in like the interactive states like trust. That's my own PhD work way back was on this topic too. And then automation bias, which is over or under reliance on AI by a human. And then situational awareness as well. So how does the human understand what the properties of the algorithm and how they relate to the context? And this work is going to look into specifically kind of human aspects. We're going to talk about a controlled experiment where we want to get at some of these ideas of human variance. It's easy to understand AI variance. You can run simulations and compute variances. But human variance in behavior can be caused by so many different exogenous factors. It's a kind of a difficult thing to figure out. And one property we're really interested in getting at is, the overconfidence factor, when people really think that they're better than AI. And, that makes us think that, if people can be overconfident and incorrectly overconfident, even if we can make great AI algorithms, we still have to go and convince people to actually use them. So our experiment tries to get towards these questions a little bit. And In particular, you guys are probably all familiar with this effect already. This is a famous paper from 1999 that talks about the effect between self-reported expertise in something and then their actual expertise. Or here, as it's mapped, reported confidence and actual experience. And what you see is on the left side, people who report very high confidence and actually have very low experience. And that's, mentioned here as like Mount Stupid. So this is the Dunning-Kruger effect, and that's what we're trying to get at in this paper. Specifically, the research questions. So we want to know, how does a person's self-assessed knowledge at a task predict the way they adhere to advice from AI, from a predictive assistant? And then we want to know, are rational explanations from that assistant effective on these people who are overconfident? So they're very specific questions. And then we want to know also if there's a relation between this overconfidence or Kruger effect, automation bias, error and accuracy, and then the level of transparency or explanation of the system. So in order to get to this, Svika, if you could give me a 10-minute and 5-minute, that would be really great. In order to get to the answer to these research questions, we employ this abstract trust game, which is known as the N-player Diner's Dilemma experiment. Most of you are probably familiar with the prisoner's dilemma, where you have two prisoners. One they can either confess or not confess, and the person who confesses will get the most reward if the other person doesn't confess. It's an abstract trust game in this form. Specifically, the Diner's Dilemma. It's a repeated choice experiment. So the scenario is that multiple people dine out together. They have the choice. They do this over many different days. They have the choice of ordering an expensive item or a cheap item. But at the end of the dinner, they all share the bill equally. So if you order an expensive item, you're kind of passing off some of that expensive cost on everyone. So there's a kind of a Nash equilibrium in this game where people get defensive and everyone will end up ordering the expensive item, but overall it will cost more for the whole group. And the kind of social good aspect would be trying to convince your neighbors to all order the cheaper item. So we leverage this game to try and understand, to try and inject some assistance from an AI and see if the AI could actually see how people interacted with that AI to answer those research questions. Here's a quick overview of what the thing looked like. So we had this dining guru, which was the AI assistant. And I'll just show a quick, I think I have a video of this here that I can show. Okay, so I'll super quickly explain what the interface was. So basically in the game, the top two left panels, people can see the current state of the game, the payoffs, what the reward will be if they order the expensive and cheap items. And there's big buttons that they can click to control that. The bottom panel shows the history of the game, where they can learn about how their co-diners are playing and what their strategy is and how that's evolved over time. And the right panel up here is where we place the automated assistant's predictions, so they can look into the future of the game and strategize and try and come up with a decision. And here's where we allow for kind of manual strategizing or automated strategizing from the advice giver. Okay, so just a little bit on the methodology. This was an open-ended experiment, so players were free to choose whether to use the advice from the assistant or not. People played 3 total games, and we recorded situational awareness and gave lots of questionnaires through the games, through each game, to try and gauge how people understood the game at different points and their strategy and so on. In terms of the participants, this was a large enough study. There was 529 participants. We used crowdsourced tool Amazon Mechanical Turk, and we used lots and lots of mechanisms for filtering this data to ensure that the people were actually paying attention and so on. Okay, you can look at it in terms of a process flow. We had the two. This was an individual user playing this game against 2 automated opponents or co-diners. So the diners would make a decision. The user would assess that decision, make their own decision, and then we would compute dining points or overall score, how well they did, basically, as the total quality of the item that they chose versus the share of the bill that they had to pay. That was the performance. So there were multiple treatments in the game. I'll run through them quickly. So we wanted to assess the impact of error, explanation, and how automated the system was. So we varied these in these 4 treatments that you can see. So for example, the one on the left has no explanation and no automation. So it just says you should order hot dog and doesn't give any explanation. And there's no automated kind of, there's no, the dining guru, the suggestion bot wasn't there either. So these were the 4 conditions. The errors were injected kind of into the behavior of the co-diners, so they're not shown in the diagrams here, but that was also manipulated. Okay, so we had lots of covariates to kind of measure this Dunning-Kruger effect. So the self-reported familiarity with the task. We measured their expertise through a quiz, and I'll show some examples on the next page of that. And then we interrupted the game and gave them a quiz to measure their situational awareness of the context of the game. To measure the outcomes, we used these McKnight-style questions, so you can see a few examples here where we wanted to get familiarity. So we asked about familiarity in 3 or 4 different ways. There was good internal consistency between the responses to these questions, and Cronbach's alpha shows a 0.8. And you can see that for trust and for self-reported familiarity. We also measured the optimal moves in the game, which was a proxy for decision success. So here's just a quick example of just some of the questions that we asked to measure awareness. Sorry for all the text, but they varied from very simple awareness questions like how much does a hot dog cost to much more complicated math-like questions about, in this given scenario within the game, what would your optimal action be given certain other behaviors. So there was a scale of kind of awareness that people had. Okay, so in order to validate this task, first thing we needed to do was to make sure that the predictions that our automated agent was giving were actually better, that the automated agent would have done better than the human users. So that was our first validation step. And then we also wanted to check that the proxies that we used for Dunning-Kruger effect actually held true. So that's H2, 3, and 4. And I'll return to that in a minute. And so the key research questions were, how does the self-assessed task knowledge predict adherence to advice? Are rational explanations from the assistant effective on overconfident people? And then what's the relationship between overconfidence, automation bias, error, and explanation? So the approach we used to evaluate was this structural equation model. I'm not going to spend time describing these in detail because I don't have enough time, but I'll get to the key results. Okay, so the first result was on validation. So here we looked at this correlational model that showed that if you look at the values, the minus signs probably are not all that clear, but it shows here that first of all, the automated algorithm did better than the humans would do, so if they followed its advice, they would have done better. And then secondly, if you look at the effect of reported familiarity on measured expertise, that was a negative effect. Reported familiarity also had a negative effect on optimal moves. And then measured expertise, the actual expertise had a positive effect on the optimal move. So that shows us that our quantification for Dunning-Kruger was actually correct. Some other key results. So we want to know, does the self-reported familiarity predict trust and adherence? And an interesting result we found from this was that people in this Dunning-Kruger group, they tended to report that they trusted the AI, but at the same time, they didn't actually adhere to the predictions of the AI. So there was a disparity in the result there, which we thought was interesting. Conversely, for the true experts, so people where we measured the expertise, there was no such effect found, so we can't really say anything about that. Okay, and then we want to know, are rational explanations effective, regardless of self-reported familiarity? And I think a good way to show this is probably just here on the next slide. So I'm going to take just a moment on this one because I think this is an interesting result. So this graph is a graph of adherence. So how did people follow the prediction from the AI, whether they followed it, to what extent, and then self-reported familiarity. And it's broken down in terms of EXPL 1 and 0. So that indicates whether an explanation was present with the AI or whether it was not present. And there's a couple of things that you can see from this, and it kind of reflects the last question from the previous paper as well. So first of all, as this self-reported familiarity with a task increases, we see this general drop-off in adherence to the predictions from the AI. But what's more interesting is the only significant difference that we could find between the presence of an explanation and no explanation, and how that affected adherence to what was being predicted. We only found that in the first quartile of results, the lowest quartile of people who were familiar. So those people who were basically, non-experts. So we think that's there's something interesting going on here with respect to explanations, and we'd like to look further into it. Okay. We also looked at automation bias. I've been told I have 5 minutes left, and I think I'm doing okay for that. So, okay, so when the system was automated, as in when it kind of didn't require user interaction to get predictions, people showed less game awareness, and that's what these top 3 arrows show here. And then we also found that showing explanation to users that were overconfident actually reduced their awareness of the game, so they scored lower on the awareness test. And that last point maybe we're positing that that's because maybe they were burdened with that extra explanation, and maybe it produced some information overload effect. That's a reasonable thing. So, so just to wrap up with a few conclusions, some insights from this. This was kind of an abstract, very abstract experiment. We kept it abstract on purpose to try and answer some of these general questions about how humans interact with AI, which is an extremely complex process, and I believe needs to be addressed in this kind of abstract way, as well as doing it in complex, more context as well. But I think there's value in doing it using these simple abstract trust games to try and understand how people really think when they're interacting with AI. So the first thing is that reported trust in a system and then behavioral adherence have a weak relationship, and we think that a way to study this further, or the right way to study this further, is to implement these open-ended kind of methodologies when we're kind of trying to study this effect. The research question, how does a person's self-assessed task knowledge predict adherence to advice? So we found that those who had the high familiarity reported adhered less. Then are rational explanations from an intelligent assistant effective on overconfident people? And I just showed the result of that. They really were only, the explanations were only effective on the lower quartile. And really, solutions for this might be to use some kind of emotional or other psychological persuasion that could maybe help people to adhere to the AI. The last research question, what's the relationship between overconfidence, bias, and system error? Really these are James's slides, so I'll just read his last point. So there's a danger in showing explanations to self-confident users because their awareness might be negatively impacted. And he's positing that this can be mitigated by requiring interaction during this kind of dialogue with the AI. But he also says that requiring interaction making the system more manual is not really a cure for poor adherence. And maybe things like non-rational methods, like maybe appealing to emotion, might be better. Okay, so that's a brief summary of the experiment. So I'd like to kind of just leave it there and open it to questions. But I also want to put one shameless plug for our second paper, which is later in the week, and it's personalized explanations for hybrid recommender systems. That's going to be on Tuesday at 5:10 in the collaborative interfaces session, which is going to be in the Pacific room. This will be presented by Piggy Cookie, and it got one of the 7 best paper nominations. So great. So hopefully there are some questions. Thank you.
Thanks, John. Great talk. I will spare you the stats questions. My question, so I see similar things when I do research on privacy and security and things like cyber victimization, right, where if you teach people about these things, they do become more aware of the problems, but they also become overconfident. So actually the million-dollar question here is that you didn't really answer, and I hope you have some ideas about this. How do you prevent people from becoming so overconfident that they stop heeding advice and do stupid stuff like running for president and things like that?
Well, so I just want to kind of clarify. Thanks for the question, Bart. So, I'm going to go back to the slide on the, well, I can, if you go back to the Dunning-Kruger slide, so there's kind of confidence, but then there's also expertise. So, you know, I would say that in what you just described, as the person interacts more and more with the system, they eventually stop being non-experts and start to get some level of expertise. So even the process of doing that is a kind of pedagogical process in itself. So they will, you know, people will actually start to learn and become, you know, more adept as they use the system. That's about the best answer I can,
I think that
give to it. So
comes close to the kind of statsy question that I had about potential nonlinearity effects between the familiarity and the expertise side, because the Dunning-Kruger is like a U-shape, right? And you didn't.
Yeah, thanks.
Is there any other question? We have time for a quick one.
I was wondering if maybe you said it and I might have missed it, but did you evaluate how good the explanations were? Like if they were intelligible, people were looking at them, if they were convincing? Because perhaps the fact that there was no effect could have been that they're not well crafted.
Yeah, so it's a really good question. I can answer some of it definitely and some of it not definitely. So I know there was a mechanism in place. If I can go flip really quickly back to the image of the diagram. So here, in the interactive tool, people had to actually engage with the explanation. So remember, this was deployed on Mechanical Turk. So this right side where it says mouse here to see my recommendation. So we factored in whether they. So first of all, they have to mouse here before they even get to see it. So we know if they were engaged with the explanation. So I know that for a fact, and I know that data was used in measuring the adherence values. But what I don't know offhand is whether users were assessed in the post-study as to what they thought of each explanation. But I'm pretty sure that was done. But I just don't know the results because I was just given the slides. What I can also say that if you're interested in a more in-depth answer of that question, the paper I just advertised for Thursday goes into really great detail on how people perceive different types of explanation in forms of text-based, visual, and so on, and content, whether it's content that comes from social things or non-social and so on. So we look at all of these different aspects with respect to how people perceive explanations. So that paper should give more insight into the question, I think. Thanks.
I guess it's time to thank the speaker again.